All right, last class talking about chemical reactions. We talked about, I believe, temperature. All right, so we talked about concentration and surface area and pressure earlier on. In the last class, we talked about the effects of temperature on the rate of reaction, and then catalysts. So we talked about that in a bit of detail, right? Obviously, as much as given in your syllabus. Uh, and then enzymes, which are biological catalysts, and then reversible reactions. Uh, and we took the example of, you know, anhydrous and hydrated salts.
Yes.
Now we're going to bring that information together with, talk about equilibrium, so what that is, and then we will talk about the industrial manufacture of ammonia and also of sulfuric acid. So I'm going to talk about equilibrium first. Now, in your text, equilibrium is sort of mixed in along with the explanation of the ammonia making process. So I'm trying to, take that out from all of that other information and present it to you separately.
Yeah.
Okay,
Yeah.
so that hopefully it makes more sense. So what is equilibrium? Equilibrium is a state achieved in a reversible reaction, right, or a point in a reversible reaction. We've already come across, we already know what, like in theory at least, what reversible reactions are, right? In which
Yeah.
the concentrations of reactants and products do not change, right? Now, given the example that we've gone over for reversible reaction, this doesn't make sense because, right, what we've seen is, oh, you've got, cobalt 2 chloride and you add water to it so it changes color, and then you heat it and so it's losing the water and so it's going blue. And this is not something that's happening on its own. Obviously, nothing happens on its own, but the thing is that it's not something that's happening reversibly, in the sense that I leave cobalt 2 chloride out on the desk, right, on my workbench, work table, and it's constantly moving between pink and blue on its own. That's not going to happen that way, right? So I'm just giving you this concept, and so when we look at some of the reactions for the Haber process, that's the name for the ammonia making process industrially, and so we'll see where this comes into play, right? So just keep in mind that equilibrium is a point in a reversible reaction in which the concentrations of reactants and products do not change, right?
Yeah.
Acha, generally, right, this happens in a closed system, right? What is a closed system? So when you're dealing with gases or anything, right, it is that nothing can enter from the outside. So nothing can contaminate your reaction, right?
So does it happen in open system as well?
And equilibrium might possibly be achieved in open system, but it would take time and it would be very delicate because any fluctuation would cause the reaction to move one way or the other, right? So basically,
Yeah.
when you're talking about a reversible reaction, right, you've got the reactant side and the product side, right? And so it's reversible, meaning the reactant can go to the products can come back to forming the reactant. That's what reversible means, right?
Yeah.
And so in open system, because
Can
there's
you
so,
please explain this? I'm sorry for
sorry,
interrupting.
could you repeat that, Aram?
Oh, I'm sorry. Like, I was asking, can you please explain this again?
It will become clearer when we get to the example. Okay, so I'll ask you to wait. If it's not clear after that, then obviously ask. So in open system, because there's so many variables, right? An equilibrium is more difficult to achieve, and even if it is, it would be very delicate and easily disturbed, right? So in a broader aspect, you might have equilibrium, right? But on a finer scale, perhaps not. Okay, now the definition, right, given the text in your syllabus, a reversible reaction in a closed system, right? And again, a closed system, right, is one in which gases can neither enter nor leave, right? So whatever you have in your reaction vessel is all that you have. Nothing's leaving, nothing's coming in. Unless you want it to leave, then you make it leave, or you want to add something, then you put it in. So it's in your control. That is what a closed system is. So a reversible reaction in a closed system is at equilibrium when the rate of the forward reaction, so we've talked about rates, we know in a reversible reaction you can go both ways. So the rate of forward reaction is equal to the rate of the reverse reaction, and the concentrations of reactants and products are no longer changing. So that is the full definition, right? Now, because you have a reaction going both ways, how do you favor one over the other? Like if I want the reaction to go from the reactants to the products, it can come back as well, but I want it to go towards the products more. So what do I do, right? And so there was this French scientist named Henri Le Chatelier, if I'm pronouncing his name correctly. Again, this is there in the text, obviously. And so he observed that there are four things that you can do to move the reaction either way in a reversible reaction, right? Which is basically shifting the equilibrium. So there are four things that can be done. The first thing that you can do is changing the temperature. How does this work? So if there's an exothermic reaction, what is an exothermic? What happens in an exothermic reaction? Can you tell me?
The heat is given out.
The heat is given out. So if the reaction itself is producing heat, right? Then what kind of temperature do you want? Do you want a high temperature or a lower temperature?
A lower temperature.
High
Exactly.
temperature. Oh, good.
Lower temperature, right? So lower temperatures favor exothermic reactions, right? Which basically means if the forward reaction is exothermic, going from reactant to product. Right, when I say forward reaction, it means reactant to product. You want a low temperature to favor the forward reaction. Right? If you keep a high temperature for an exothermic reaction, it will favor the reverse. Because if the forward reaction is exothermic, the reverse would be endothermic, that's right. And so
Yeah.
having a high temperature would actually cause the products to go back towards the reactant side. So they'll split or rearrange or whatever's happening, and you'll have more of the of the reactants forming and less of the products.
Okay.
So if there's a high temperature, right, the reverse reaction is favored. So there needs to be a balance now. Now try bringing all this together. Increasing the temperature increases the rate of reaction, right? Why? Because it increases the number of collisions, number of successful collisions. Yes, but you also need to keep in, right, if it's only a forward reaction, right, and so it won't matter as much, because, right, even if you're keeping a high temperature and the reaction itself is exothermic, what the problem will be is that so much heat will be generated, you need to make arrangements to, dissipate that heat, right, to lose that heat or to use it to do something else, right, because obviously if something it's very very hot, you're talking about multiple hundreds or maybe thousands of degrees centigrade in temperature, and so that is a problem in itself to right, to handle. So if it's just a one-way reaction, then it's not as complex. But if you're dealing with a reversible reaction, then yes, increasing the temperature will increase the rate of reaction, but you also need to keep in mind if it's exothermic or not, right? Most reactions are exothermic. So, right, if it is exothermic, you don't want the temperature to be so high that it goes the other way. So you're going to keep a high temperature, keeping in consideration how much heat is being generated by the reaction itself. Okay. Now, obviously, right, you're not designing an experiment. Like, I mean, you will be designing experiment in paper 4, but, right, you're not like doing industrial work right now. So this is a concept that needs to be clear, because it can be asked to you in your exam. Why would, like, would you keep a high temperature or a lower temperature, right? By saying low, it doesn't mean you're keeping like 20 degrees centigrade, obviously, right? Low by industrial standards,
Yeah. Okay.
right? So 200 degrees or 250 degrees centigrade is low by industrial standards, where you have temperatures like 750 degrees centigrade, right?
Yeah. Yeah.
Okay. Second, you have changing the pressure, right?
So if it's exothermic, there will be low pressure.
Oh no, this does not have anything to do with exothermic.
Okay.
So changing pressure, right, for gases. So if you increase the pressure of a system, and so remember, for gases, increasing the pressure increases the rate of reaction, right? But you are dealing with a reversible reaction. So if you increase the pressure, the reaction with the fewer number of molecules will be favored, right? So for example, if you've got 3 reactants going to make 2 products, for example, you increase the pressure, right? And so the forward reaction will be, so let's make this reversible, right? And so the forward reaction will be favored when you're increasing the pressure. Why? Because there are less molecules over here on the product side.
Okay.
Okay.
Yeah.
Then you have changing concentration. Now, obviously, right, whichever side has more concentration of molecules will react more and form, the other. So if you've got more concentration of what you call it, reactants, then you will get more product. All right, so you've got higher concentration of reactants will give you more product. So you're favoring the forward reaction. Make sense? Simple?
Yeah.
Okay. And then finally, it's using a catalyst. Right? And so, I mean, that doesn't really need an explanation because, right, we already talked about catalysts, and nearly all industrial processes use catalysts. Okay. And
Yeah.
the thing to keep in mind about a catalyst, it increases the rate of both forward and reverse reactions. So why are we using it? Right, so the position of the equilibrium is not affected. So then what's the point? The point is that, as we talked about, the catalyst makes the reaction happen more quickly. Right, so you're getting products more quickly. It's increasing the rate of reaction. So you adjust the other things, the concentration, the pressure, and the temperature to favor the forward reaction. The catalyst is going to make it happen more quickly as as compared to happening without the catalyst. And so you're going to get products in lesser time. Okay, now some of this makes sense, some of this is not very clear at the moment. And so let's talk about the Haber process. Put everything we've talked about so far into application. Right, theoretical application, but application nonetheless. So Haber process is the name for the industrial, right, the process of the industrial manufacture of ammonia. And so what happens in the Haber process is that you take nitrogen and hydrogen and react them to form ammonia. Right, so ammonia is formed by reacting nitrogen and hydrogen. Not hydrogen, no, hydrogen. So the first step of the process is getting the nitrogen. So where do you get the nitrogen from? So as we know, nitrogen is in the gaseous state. Generally, you can have liquid nitrogen, but it's super cold and it's used for freezing and cooling, right? So the nitrogen is the only thing they're mentioning over here, so don't get confused, right? Because it's going to come later on in chapter 12. And so what they mention is that the nitrogen needed for the Haber process is obtained from uh, the atmosphere. So we know that one of the gases in the atmosphere, in the air that we breathe, is nitrogen. Most of it is oxygen, right? Then you've got, sorry, wait, why am I confusing myself? Well, you've got oxygen, carbon dioxide, nitrogen. Those are the major players, and then you've got bits of others. So, right, you get it from the atmosphere. How? By the fractional distillation of liquid air. What is fractional distillation? You've kind of come across this when we talked about the fractions of crude oil. Remember?
Yeah.
Right, that crude oil is heated to a certain temperature, and then so the fractions, they move up the column. As they keep moving up, the temperature keeps decreasing, and so they start
Yeah.
condensing and separating. That's basically the concept of fractional distillation, right? Applied to a much wider scale in the separation of fractions from crude oil. But so what they're doing is, right, the fractional distillation of liquid air, right? So they liquefy air, and then they separate the oxygen and the nitrogen and everything else. So that's where the nitrogen is coming from. Then comes hydrogen. So how do you get hydrogen? Hydrogen is obtained from methane. Right, so you're not immediately reacting nitrogen and hydrogen. First, you need to get those, right? And so you are reacting methane, which is something we have come across again in the chapter we were talking about fuels, and you're reacting it with steam. So that is gaseous water, right? Hot gaseous water, not just gaseous water. And so that in itself is a reversible reaction. So let's write that down, right? You have, go to the next page. You have methane plus steam. It's a reversible reaction, right? Giving you hydrogen and carbon monoxide. So this is what it looks like. You have CH4, which is a gas, that's methane, and you've got H2O, but as a gas, and you are getting hydrogen and carbon monoxide. You guys want to balance this?
Well, H2 is balanced.
H
Carbon is,
H2 is balanced.
yeah.
How
And so H2 is on the reactant side and H2 on the product side.
are you forgetting the H4 over here?
Yeah.
Like 3 on the product side.
Anything else?
She said on the product side.
This is the product side.
Oh, okay, okay, yeah.
It's balanced.
It's balanced. Right? So, right, this process is known as steam reforming. Okay? And as you can see, obviously, it is a reversible reaction. Right? So, the reaction that's, as I already mentioned, and you understand that the reaction going from left to right is right, going from reactant to product in this case for us is known as the forward reaction. Okay.
Yeah.
So what happens in this, right, is the reaction occurs at 750 degrees centigrade at 3000 kilopascal. So what are the conditions for this reaction? You have 750 degrees centigrade, 3000, not pascals, kilopascals, right? So 3000, which is basically 3 million pascals. Okay. Or in other words, it's 30 atmosphere. Right, so 30 times the atmospheric pressure. And it also uses a nickel catalyst. All right, so something for you to perhaps remember. Now, right, carbon monoxide is produced and carbon monoxide is toxic. We don't want this. So what happens is that the carbon monoxide is further reacted, right? Or in this case, let's say it's reduced with, by the unreacted steam to produce more hydrogen gas. So you've got carbon monoxide plus steam this is also a reversible reaction, and you're getting hydrogen plus carbon dioxide, which is not as bad. This is what it looks like. You've got CO2, CO, which is a gas, and H2O, also a gas, giving you hydrogen gas and carbon dioxide gas. Is it balanced?
No. It's not.
Really?
Yeah.
Carbons 1, oxygens 2 and 2, hydrogens 2 and 2. It is balanced.
Okay.
Okay, so what's happening over here, right? I believe I said the carbon monoxide is reduced. Carbon monoxide is not reduced. So let me correct myself. Right, the carbon monoxide is oxidized. As you can see, it has a single oxygen here, and now it has two oxygens over here. So the carbon monoxide is oxidized to carbon dioxide. The steam is reduced to hydrogen. Why am I saying, or why, chemically, why is the steam reduced? Can you explain that to me?
Can you please repeat the question?
The steam has been reduced to hydrogen gas by carbon monoxide. How has the steam been reduced? Like what over here, what's happened over here that's telling you that steam has been reduced? Remember oxidation reduction, right? We're saying reduction has taken place for steam. What tells
It has
you
lost
it has lost?
oxygen.
It has lost
Oxygen.
oxygen. Exactly. Right? So over here, it had oxygen, over here, no oxygen. So one of the uh, definitions of reduction is loss of oxygen, right? Okay. Now we have our hydrogen and our nitrogen. Okay. Now we are going to make ammonia. So right, this reaction is simple, so to speak. You take nitrogen and you take hydrogen, and this is also a reversible reaction, and you're getting ammonia, right? So you have N2 gas plus H2 gas, giving you NH3, also a gas. You guys want to try balancing this?
Two on the product side.
Okay, if I'm putting 2 on the product side, so I've got 2 nitrogens on the reactants, 2 nitrogens on the product, so that's fine. I've got 2 hydrogens on the reactant and 6 hydrogens on the product side.
So you're gonna put 3 over there.
Good,
Yeah.
good. Okay, so this is the reaction that is making ammonia. Now there's certain things, right? So bringing back everything we know about rate of reaction and whatchamacallit, uh, right, equilibrium. So this is an exothermic reaction. The reaction is exothermic, right? The enthalpy change is negative, right? So the delta H equals to minus 92 kilojoules per mole, right? And so what you want lower temperatures to favor the forward exothermic reaction. And so what are the conditions of the reaction? Right, the reaction is carried out at 450 degrees centigrade, which, as you will agree, is definitely lower than 750,
Yeah.
right?
Yeah.
And is carried out at 20,000 kilopascals. That's pressure, and it uses an iron catalyst. Now, if you take a look at the book, I will put that on screen. So just give me a sec. Can you see that?
Yes.
Yeah.
And so what they're showing over here is, 450 degrees is not the best temperature, right? You're not getting as much ammonia, percentage yield of ammonia, right? At
As much
equally,
as 350.
yeah. So right, you've got 20,000 kilopascals, and so right, it's actually pretty low, right? They mention over here that the yield of ammonia is only 15%, right? So there's a lot of unreacted nitrogen and hydrogen, and so that's recirculated to keep on producing more ammonia, right? But in one go, only 15% of the nitrogen hydrogen is reacting to give you ammonia, which is very low, right? So you're talking about 20,000. So you're talking about like way down here, right? It's like 200,000, and you're talking about 20,000. Obviously,
Yeah.
not that high.
Yeah.
So, right, you could increase the yield dramatically by reducing the temperature or increasing the pressure to these high levels. But again, right, what's the point is that you want it to be economical, meaning that you want the conditions that are manageable and don't cost as much as the final product will be able to, will be sold for. So you want to make a profit. So having, high pressures and lower temperatures is going to cost a lot more than the actual, ammonia will get you money for, right? When you sell the
Yeah.
ammonia. And so it won't be worth it then, right? You're getting more ammonia, yes, right? But at the end of the day, it's not either worth it economically, or it's not worth it in terms of, being able to maintain those conditions. So having like 300,000 kilopascals of pressure is difficult to maintain, right? You need very, sophisticated and safety requirements of your setup to be able to withstand those kind of pressures, right? And so what the industry does obviously reaches like the sweet spot which works, right? So it's not the best, but it's getting work done, and you're making enough to have a profit. You're able to sell it with a profit, because at the end of the day, it's industry, so it's commercial, it's about money, right?
Yeah.
Aram, is that clear?
Yes.
Right? And so, right, this is happening in a closed system. Obviously, you're not reacting nitrogen hydrogen out in the open. You're reacting it in a pressurized container, because you've got 20,000 kilopascals. So it is a pressurized container, right? And so, right, in a closed system, which is, your gases are not leaving on their own and nothing is entering from the outside on its own, unless you want it to enter, or you want something from the reaction vessel to leave. And so equilibrium means that, the rate of reverse and forward reaction is equal, it balances out, and so the concentrations are not changing. One thing to, just highlight, because the process continues to happen, the equilibrium is said to be dynamic. What does that mean? What that means that when it reaches equilibrium, right? So the rates balance out, and the concentrations of the reactant and product, they do not change. They're not saying that they balance out. They do not change. So they reaches a point where the concentration, meaning, the amount of reactant you have and the amount of product you have, is not changing. But does the reaction stop happening? No. Right?
Okay. Yes.
Right, so you've got nitrogen hydrogen reacting to form ammonia, and you're still having ammonia that is going the other way. It is breaking up to form nitrogen hydrogen, so that is continuing, but it's not causing a change in the concentrations, or, which one is going ahead and which ones. So because the reaction does not stop, it continues to happen, and so it's called dynamic equilibrium. Does that make sense?
Yes.
Yes.
Okay, so let's go back to the whiteboard. So with
I
that,
have a question.
yes.
Why is it necessary to balance the equations?
Why is it necessary to balance the equations? It's necessary to balance the equations because when reactions happen, they happen in certain proportions, right? So when a reaction is happening, 3 molecules of hydrogen will be needed to react with 1 molecule of nitrogen to
To
form
create the expected result.
to form ammonia, right? Why? Because in this case, right, both ammonia and hydrogen are diatomic, right? So you can't just get N, right? You can't get a single ammonia atom. It does not exist that way, right? It exists as a diatomic, and so does hydrogen, right? But ammonia has 3 hydrogens, right? And so these are covalent bonds. So what are you going to do? You're going to take, like, okay, I'm going to take a single atom, and I'm going to take 3 separate atoms of hydrogen. I'm going to react them, and I'm going to get this. That's not how it works. Okay. So when the reaction happens, if you have the correct proportions of reactants and products, 1 molecule of nitrogen will react with 3 molecules of hydrogen to give you 2 molecules of, that is how the reaction will happen, right? So you will get 2 molecules of ammonia out of this. How does that make an effect? For example, you have 10 molecules of nitrogen, right? And 25, right, molecules of hydrogen. How many of these do you think will react?
10.
No. Okay, let's go to the next page for this. Right? So let me rewrite that. Big asterisk over here. You have 10 molecules of nitrogen and you have 25 molecules of hydrogen. They won't react because what you want is NH3. Right? So let's look at this. You've got 20 atoms of nitrogen and you've got 50, right, atoms of hydrogen, right? And the ratio of the atoms is 1:3. So how do you fix that over here? 320s are 60. You don't have enough. That means that all of these guys will not be reacting. Some will be left over, right? So let's divide 50 by 3, right? What do you get when you divide 50 by 3?
1, 1, 2, 1, 3, no.
150.
1, 9 point,
50 divided by 3.
1, 9, 19 point, I guess.
50
9,
multiplied by 3 is 150.
50 divided by 3.
Oh, you said
19.3, I
divided.
guess.
Did I say multiply?
I heard you say multiply.
Okay, divided, right? Maybe
16.6?
yeah. So 16.6. So let's say 16 because you're not getting 0.6 of an atom,
Hmm.
right? If you're
Yeah.
if you're going to split the atom, it's going to go boom, right? So not good. You'll end up making a hydrogen, making the hydrogen explode. So you got 16 of these guys. So you're having 16 of these, right, in the 3 part. And so, right, how much can you get over here? How many do you think will be utilized over here? All right, let's make this simpler. Let's make this simpler. Uh, right. Let me just remove this. So we know that the ratio is 1:3, right? And so you're only going to have, right, 25 divided by 3 is 8.333. So you're going to have 24 of the hydrogens reacting with 8 of the nitrogens, right? And you will end up with uh, how many? Right? 20, 16. You will end up with 16 molecules of ammonia. What that means is that 2 molecules of nitrogen and 1 molecule of hydrogen will remain unreacted. Why? Because that's the proportion it works in, right? So balancing does not mean, oh, I can put any amount of the reactants and expect to get 100% yield. That's not going to happen, right? Unless you have the exact amount, right? So if you're putting it in 1:30, you're putting 10 nitrogens and 30 hydrogens, right? Then you will get 20 ammonia, right? And this is theoretically. In reality, that's not happening. You're only getting 15%, but theoretically, right? Because you need, so in this case, there's no unreacted, uh, molecules. Does that make sense, sir?
Yeah.
So the reactions happen in particular proportions, right? And So again, the reason behind that is really the chemistry, the bonding, right? So because in this case, they exist as diatomic. Another example, which I believe I gave when we were talking about bonding. So just to digress a bit, right? For example, you are making magnesium chloride. Now this is balanced, right? But then the question is that why do we need two chlorine, right? Why can't we just have MgCl, for example, right? And the reason for that is that the valence electrons of magnesium, there are two of them, right? And for chlorine, there's 7, right? And so to become stable, in this case for ionic bonding, magnesium needs to give up 2 of its electrons. Now, if it gives 1 of its electrons to a single chlorine atom, yeah, that works, right? Chlorine is happy, but magnesium is not, because it still has 1 valence electron, right? It wants to give that up as well. Otherwise, there's no point. It was unstable, right? It had an incomplete shell with 2 electrons. It still has an incomplete shell with 1 electron. So it's not really making a difference, right? And so you need the other chlorine atom as well, right? With those 7 electrons, it's going to accept the other electron from magnesium, and you're going to have MgCl2, right? And so reactions happen in certain proportions. And that is why in balancing, what we look at is the total number of atoms, right? Whether it's written as a multiple or as a subscript, right? As a factor or as a subscript, doesn't matter, right? So, okay, 2 hydrogens times 3, that's 6 atoms in total. That's what we're looking at, right? Again, right? So does
Thank
that
you.
clarify things for you?
Yeah.
Okay. Now we do have a bit of time on our hands. Can I push through with the right? There's detail about the exact conditions to that affect equilibrium in.
Can that detail be finished in 12 minutes?
Oh no, I'm leaving that detail to you. So just read it. It's nothing technical, right? I am just quickly going over the contact process, which is the industrial manufacture of sulfuric acid.
Okay.
So that is the industrial manufacture of sulfuric acid. So where is sulfuric acid used? It's used in paints and fertilizers and detergents and stuff. First of all, what we do is you take sulfur and you burn it in excess of oxygen in air, right? So sulfur plus oxygen gives you sulfur dioxide. That's the first step, right? And so you've got sulfur, which is a solid, plus O2, right, which is a gas. And so this guy is coming from the air, and you are getting SO2, which is a gas. Okay, and that's balanced, so that's good. So sulfur dioxide can also be obtained from ores, like zinc sulfide. So that bit is given in the text. Next, right, the sulfur dioxide is heated with more oxygen. So this is step 1. Step 2, sulfur dioxide plus oxygen, right? And this is a reversible reaction. So the first reaction wasn't reversible, right? So this one is a sulfur reversible reaction, and you are getting sulfur trioxide. And this is an exothermic reaction. So the delta H, the enthalpy change, is minus 197 kilojoules per mole. Right, so you've got SO2, which is a gas, plus O2, which is also a gas, giving you SO3, also a gas. And for the sake of time, that's how you'll balance it. Okay. And so the reaction conditions for this is that the temperature is 450 degrees centigrade. So it's 450 degrees centigrade, and the catalyst used is vanadium 5 oxide. So vanadium, that's not V for vanadium, that's 5, the Roman 5 oxide, right? Which looks like this. Chemically, it is V2O5.
Okay.
This V is for vanadium. This V is for the Roman 5, just to clarify that.
Okay.
Okay. Now, see, right? When you talked about pressures earlier, right? See what's happening. When you keep the pressure high, the side with the lesser number of molecules is favored, right? We talked about equilibrium. And so look at this reaction, right? You've got 4 molecules over here and 2 molecules over here. So when you've got high pressures, right? Or in this case, the condition was that you have, right? Just a sec. Uh, yeah, right. So you've got right. You're carrying this out at 20,000 kilopascals, and so you're moving from more number of molecules to less number of. Sorry, I was just confused in a bit. I was double checking something. Right, and so similarly over here, what you have is you've got more molecules going towards less molecules, right? You've got 3 going towards 2.
Could you say you said the V was for vanade what's that called?
Vanadium. The reason I'm clarifying that is because the symbol for vanadium element is V, and this V is also right. So there's confusion. So that there won't be any confusion. This V is for the Roman 5, right? The 1, 2, 3,
In this
4.
situation, is it the symbol or is it the number?
This is the number,
Okay.
and this is the symbol.
Okay.
Okay. Then finally, you react sulfur trioxide with water to get sulfuric acid. So that's step 3. In fact, right, step 3, sulfur trioxide plus water gives you, uh, this is not a reversible reaction, so sulfuric acid, right? And so what that looks like is SO3, which is a gas, plus H2O, which is a liquid, giving you H2SO4, which is a liquid, right? And it's all balanced, and that's it.
Like, how are we supposed to know whether a reaction is reversible or not?
You yourself will not know. So, for one thing, the reactions that are being given to you in the syllabus, right? You're supposed to know those are reversible, and then rest, if they give you something unknown in the paper, they will mention that it's reversible,
Okay.
right? It's not, there's no formula or rule as to say which reaction is reversible and which is not. Okay.
Yeah.
Okay. And right, so the pressure for this, it's 450 degrees centigrade, as I mentioned. You're using vanadium 5 oxide, and 200 kilopascals is the pressure. Right, so these are the conditions for the entire reaction, like all of it. Okay.
Yeah.
Okay. And that's the end of the chapter. So congratulations.
Thank you.
All right. So tomorrow we begin with chapter 11, right, which is chemistry of the environment. Before that, right, I'll ask you to read through the part that we've covered today. If there's anything that's unclear, perhaps, then ask me tomorrow. If everything's good, obviously, then we will carry forward.
And which detail part that we have to read?
Just start reading from manufacture of ammonia.
Okay.
Just read manufacture ammonia. That covers the equilibrium part as well, the detail part that I mentioned. I'm saying detail because they explain it. I explained it as well, so I didn't go over it again. And then the contact process. So read through all of that. If it's all good and clear, well and good. I may have missed out some minor point, right? So that you'll get there from the text. And if there's any confusion, we'll clarify that tomorrow. And then we'll start with the next chapter, which will be chapter 11. Okay?
Yeah.
Okay.
All right.
Okay. Allah Hafiz.
Allah Hafiz.
Allah.